So we've spent a lot of time looking at convergence of series. Our goal is to determine if a series is absolutely convergent, conditionally convergent, or divergent just by looking at it, by inspection. To that end, we want to compare two things. We want to look at the numerator versus the denominator, and we want to look at the factors. This is all in the general term. Factorial factors dominating exponential factors, dominating rational or radical factors. So we're going to consider the general term. Overall, we're going to consider the numerator versus the denominator. We're going to consider factorial versus exponential versus rational or radical. We also want to remember that there are other things that sit outside of this hierarchy, like alternating. Alternating is another way we can get things to zero. And we also want to remember that when we're coming up with series at random, the fact that they fall directly into one of these categories, nice and neat, is not going to happen. So we have our comparison tests. There's also one called the root test, which I don't usually cover. I usually don't think of it until the very end when I'm doing the summary, and it's very niche anyway. All right, so we need to think about the forms that we're looking at here: factorial versus exponential versus rational or radical. So in the rational and radical category, we're observing a fixed power of, let's say, an increasing base, n to a constant. So rational and radical, this is a fixed power of an increasing base. A fixed power of an increasing base. So n, the part that's growing, raised to some constant. This also includes the radical part, because if that constant is a 1/2, then we just have a radical term. Fixed power of an increasing base. So even though our base is growing big, our exponent is staying where it is. In the exponential category, we have an increasing power of a fixed base. So something like b, or let's say r to the n, a common ratio raised to an exponent. One of the major points of your algebra class and your pre-calculus class was to demonstrate that a fixed base, even a small one, a fixed base that's going to increase, something even slightly bigger than 1, will in the long run dominate a fixed power. Increasing your exponent is more effective than increasing your base. So we spend a lot of time looking at this, looking at graphs of exponential functions and watching them grow super fast compared to any polynomial or rational or radical function. I guess with rational ones, there are fixed values. We're talking specifically about n going to infinity, not play that certain values of n where the function is going to infinity because it's undefined. We're talking about n just growing and growing. Factorial is kind of a combo of those two. We're increasing the number of factors, and the size of each factor is also increasing. So factorial is kind of like a combination. To use this framing, it's kind of an increasing power of an increasing base. The number of factors is increasing, and the size of those factors is also increasing. Increasing number of increasing factors. The increasing size of the factors means it's like the base is increasing, and the increasing number of factors is like the power is increasing. Our goal is to look at how things are going to zero. So when we're looking at numerator versus denominator, we want to make sure that they're going to zero, and we want to make sure that they're going to zero faster than the harmonic series. So we're kind of like looking for which one is going to win. So numerator and denominator, we're thinking about which one of these is winning, and then factorial versus exponential versus radical. Radical, how is this winner winning? The tools that we have for rational and radical, we are just looking at P series. We just care about P series. For exponential stuff and factorial stuff, we care about the ratio test. At the lowest level, we've got our rational and radical factors, where we just think about comparison with the P series, not actually being a P series, but comparison with P series. The other thing that we might consider here is alternating. And then for exponential and factorial, we have the ratio test. So this gives us a little bit more insight into what goes to zero fast enough. Can we compare the series to itself by using the ratio test? For exponential and factorial factors, yeah. We can compare the series to itself. We can just look at the terms and we can just look at the ratio of consecutive terms and see what's happening there. That doesn't work on rational or radical. We have to bring in some kind of outside thing to compare it to. But for exponential and factorial, we get to compare the terms of the series. We get to compare the series to itself. We don't have to bring in some outside series that we know about. In the category of numerator versus denominator, we want to think about whether the numerator is dominating, whether there is balance, or whether the denominator is dominating. What's winning? So for numerator versus denominator, we're thinking, does the top win? Is there balance, or does the bottom win? When I say top wins, I'm thinking the numerator is dominating over the denominator. The numerator is growing faster, so the terms are going off towards infinity. When the bottom wins, that means the denominator is growing faster and the terms are ending too. And then balance means the terms are kind of going at the same rates and will have a constant, a non-zero constant, as far as the ratio of the numerator to the denominator. Let's look at some examples and think about what's going on. Go over the thinking. So here the terms aren't going to zero. All we have is n squared. The terms don't go to zero. Diverges. In the category thinking in terms of numerator versus denominator, the numerator has an n squared, the denominator has an n to the 0 power. If we bring balance to things, n squared over an n cubed, this is just polynomial business, or this is just rational. So now we're thinking in terms of p series. So our thinking, well, First of all, we see n squared over n cubed. We know that this one diverges by comparison with the harmonic series. Here, the terms are going to zero, but they're not going to zero fast enough. So the terms aren't going to zero fast enough. In the first one, the terms are just not zero. There was imbalance between the numerator and denominator. Here, there's a not enough imbalance in the denominator. Now that we have n squared over n to the fourth, now we have absolute convergence. Here we would make a comparison with the series 1 over n squared. So the terms are going to zero faster than the harmonic series. This is based on the trust that there is not a term in stuff that is degree higher than 2. That would be cheating on my part. So thinking in terms of the balance and n squared numerator, if we think of this n squared as the original n squared is n squared over 1, which is an n to the 0 power. Here the terms are not going to 0. I tried to balance it out by putting some stuff in the denominator. I tried to divide my way towards convergence. I use an n cubed. That's not enough. The terms are going to 0, but not faster than the harmonic series. So they're not going to 0 fast enough. The series diverges. So I try to balance it. I try to put a little bit more stuff in the denominator. I go with the n to the fourth. Now I've got overall of 1 over n squared. Now we get absolute convergence. So here, I grabbed convergence. I balanced things out to get convergence by using a polynomial, but I had to use a big enough polynomial. Another strategy is just put underneath the numerator something that will dominate, like an exponential. N squared over 3 to the n is going to be absolutely convergent. 3 to the n is factorial. N squared is rational. We can see this is going to be absolutely convergent. The limit from the ratio test will be 1/3. And 1/3 is less than 1. So that says the ratio test says this is absolutely convergent. We balanced out the n squared going to infinity with a 3 to the n going to infinity, and that 3 to the n is going to infinity faster than n squared. I've increased, in the numerator, I have a fixed power of an increasing base. In the denominator, I have an increasing power of a fixed base. That wins. When you're complaining about D&D, you don't want to say linear fighter. Sometimes I've heard people say polynomial wizard. That's linear is polynomial. That's misleading right away. Even if you put linear, your fighter, if you upgrade from linear to a higher degree polynomial like quadratic, even if you start making quadratic fighters, casters are exponential. So there will not be balance in the long run. The most important thing that we notice about this, if there's other stuff, even if there's other stuff going on, is that if it's an n squared over 3 to the n, if the most powerful thing that the numerator brings to the table is an n squared, and the most powerful thing that the denominator brings to the table is a 3 to the n, that you recognize that this is absolutely convergent. You want to recognize that because you know that the limit from the ratio test is going to be 1/3. Then higher level than that, you'll want to be able to run the ratio test to show that the limit from the ratio test is 1/3. But I don't want you to start writing down a ratio test until you know what the limit from the ratio test is going to be. So in this one, we're thinking the exponential 3 to the n dominates, the exponential denominator dominates the rational numerator. Any questions? It's not about writing limit as n goes to infinity and filling in all the forms. It's about looking at the series and knowing converges versus diverges and how you would get there if you were pressed to get there. As soon as I wrote 3 to the n on top, you knew I was probably going to write an n to the, I was going to write n squared on the bottom. If we flip things around, that's just going to flip the limit from the ratio test. So if we put the exponential on top and the polynomial in the bottom, diverges. We know that the limit from the ratio test is 3, and 3 is greater than 1. In this case, the limit from the ratio test is 3, and the terms don't go to 0. The limit of the terms heads to infinity. The terms go to infinity. This is just the reciprocal of the previous, where the exponential numerator dominates the quadratic denominator, the rational denominator. Two factors of 10 to the 27 is not significant compared to 10 to the 27 factors of 3. Now we can balance out this 3 to the n. We think in terms of balance. Let's go from 3 to the n. Let's put in the denominator of 5 to the n. And we're back to absolute convergence. The limit from the ratio test is 3/5. 3/5 is less than 1. This series is absolutely convergent. Now we're comparing exponential to exponential. The denominator exponential is bigger than the numerator exponential. Just like with the rational factor, I had a rational factor on top, I had a rational factor on the bottom. I had to look at what they were and see how they compare. Now that I've got an exponential factor on top and an exponential factor on bottom, I have to look at which they are to see how they compare. Five to the n over 3 to the n is still balanced between exponential and exponential. They're on the same level, it's just that the numerator is winning. This is two NFL teams competing. Exponential versus polynomial is like an NFL team competing against a top one. I should switch to basketball so kids don't get hurt so much. This 5 to the n over 3 to the n is two NBA teams competing. Exponential like a 3 to the n over an n squared. That's an NBA team competing against a local junior high. Now, if the 3 to the n, we can try to throw things out of balance. If we throw something into the denominator that's weaker than an exponential, it doesn't matter. The ratio test. So if I throw in a polynomial, I say call in some reinforcements, 5 to the n over n squared, 3 to the n, still diverges. The n squared does nothing. The limit from the ratio test is still 5/3. The ratio test is going to ignore the n squared. The limit from the ratio test is 5/3. This is an NBA team losing and calling a local junior high and say, hey, we need some help with these guys. And they're not going to be a factor in the game. I mean, they're going to increase the cuteness factor. And the 5 of the n team may let them score a few times. But really, they're going to say, but we're really still playing the NBA, so we still have to. So like the N squared team, they showed up, but nothing really, they don't really get anything. So hopefully 5 at the end of the game, it's like, oh, hey man, good game. Here's some jerseys and swag, but you lost. You did not help your 3 to the end team at all. This is still a balance between exponential factors. So what can defeat this 5 to the end? Clearly, let's see, I'm already at the NBA. Shit. Space Jam. Haha, we're so badass. I'm sorry, what? N factorial. We've dropped the factorial. Now the comparison, now it's back to a question of dominance, not just comparison, but dominance. 5 to the n is an increasing number of factors of a fixed base. N factorial is like increasing factors, but of an increasing base. The next is when n is 10 million. 10 million factors of 5 is nothing compared to 10 million factors, most of which are bigger than 5. There's the 1, 2, 3, and the 4 that are smaller than 5. There's the 5 to the 5 that cancels out. But then the rest of the factors are all bigger than 5. So we're back to, let's see, the denominator is taking this to 0 faster. So the limit from the ratio test is 0, which is less than 1. The factorial denominator dominates the exponential numerator. We know that the series converges because of the ratio test. The terms are going to 0, and they're going to 0 fast enough. They're going to 0 ridiculously fast. Factorials are very powerful. It's like just like in Space Jam. It is cartoons, and cartoons can literally defy the laws. They're not bound. So even if 5 to the n calls upon their junior high teammates or previous junior high opponents, and they come in for backup, this is still absolutely convergent, and the limit from the ratio test is still 0. But hey, those junior high basketball kids got to play in space. That's pretty cool. I think I would consider that a win. If we put the factorial in the numerator, now the limit from the ratio test is going to go to infinity, and so the series diverges. The limit from the ratio test will be more than 1. The limit doesn't exist. The limit goes to infinity. That counts as being more than 1. In this case, the terms are not going to 0. That's what's happening. When we look at that factorial growth, it's being divided by even the product of polynomial and exponential growth for large values of n, that doesn't matter. The terms aren't going to zero. Now I've got an n factorial in the numerator. The only way to bring balance is with another factorial. And so I want to introduce this kind of factorial. This is a 2n factorial. This is more factorial than an n factorial. From an intuition standpoint, notice in the numerator we have n factors. In the denominator, we have twice as many factors. Let's actually see the ratio test working on this one. We'll take the limit as n goes to infinity of the absolute value of n plus 1 factorial Actually, I'm going to do it this way. Like we were doing last week with the ratio test, I'm going to do an plus 1 times 1 over an. That's an plus 1 divided by an, but conservative versions. The important thing that we want to notice here is that it's a 2n factorial. The first thing that happens is the 2. 2, we multiply 2 times n, and then we factorial. That's the order of operations here. Even if there's no f in order of operations, PEMDAS doesn't have an f in it. The parentheses are telling us what's going on. Multiply by 2, then factorial. So this factorial down here is kind of important. This factorial down here is a 2n plus 2 factorial. This is important because our strategy is to write the bigger factorial until we get to the smaller factorial. So here I've got this 2n plus 2 factorial. So when I start writing the bigger factorial, I start at 2n plus 2. The next factor is 2n plus 1. Then the next factor is 2n factorial. And that's where things cancel out. So I think of the 2n factorial, or the factorial of 2n. It leaves behind 2 factors of n. Meanwhile, in the n plus 1 factorial, I write the bigger factorial until I get to the smaller factorial. So I take n plus 1, and the next factor is n factorial, and then they cancel out. So in the numerator, we have left behind an n plus 1. And in the denominator, I have a 2n plus 2 and a 2n plus 1. So here, the 2n factorial, that much bigger factorial, means that the limit that the terms are going to 0, and the limit from the ratio test is going to be 0, which is less than 1. So this series is absolutely convergent, and the limit from the ratio test is 0. So that 2n is acting like a bigger factorial. Notice that the 2n factorial left behind 2 factors of n. And the n factorial, when normally n factorials leave behind 1 factor of n. Normally factorials leave behind 1 factor of n. Tomorrow, we'll look in a little more detail about this n factorial and this 2n factorial. It's going to feel super contrived, but 2n factorial is a thing that actually happens, so we must be prepared for it. All right, that's going to do it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing.